Hi Chem Kids! The goal of this video is to help you start to understand what large covalent structures look like and how to interpret them and draw them. Next year, you're going to walk into biology on the first day of school and your teacher is going to draw some giant structure right on the board. And I don't want you to be thinking to yourself, oh man, Miss Baldiga, you totally tricked me into thinking all covalent molecules are these small, simple structures. In reality, we start with the smallest ones in 9th grade so you can start to understand how many bonds different atoms make, and how they all fulfill the octet rule. But when you walk into biology next year, you're going to have a chance to start thinking about not just tiny molecules, but giant important molecules like cholesterol, this giant, really important molecule that you hear about at the grocery store and at your doctor's appointments, and also plays a really important role in your biology. And you're going to spend all this time talking about these things that form in ring structures like glucose and fructose and all these important sugars that run your body and power your body and are super important for energy. And so what we want to do today is not totally master all these structures, but start to understand what pictures like this and structures like this are telling you about what kind of atoms are in those molecules. And that way next year, you can focus less on drawing the correct structures and more on interpreting the shape and the bond angles and the roles they play in biology, in your body, and in nature, and in medicine. Hopefully by now you started to notice that chemists and scientists in general love shortcuts. Whether it's writing really long electron configurations or writing really long formulas, we like to simplify things as quickly as possible so that the readers can get the most important information right away. The same is true when we're drawing structures. Instead of drawing every single atom and every single giant molecule that contains thousands and thousands of atoms, scientists have come up with a shortcut, and we call this a skeleton drawing because it's showing just the basics and most important information. And you're going to notice next year that the skeleton drawing oftentimes looks something like this. This zigzag motion is very common in large structures of organic molecules. And we're going to learn a really important rule about where carbon is located in these structures, because we learned in the earlier reading that all organic molecules have lots of carbons in them. And so this picture is basically saying, imagine it's full of carbons, but I'm going to save some time by not having to draw them. So the rule for where you're going to put carbon whenever you see this sort of skeleton structure is carbon always goes at ends and at bends. So what does this mean in the structure above? Well, carbon is always located at the end of a line. So that means a carbon is there and a carbon is there. The bends means that carbon is also located at any time that the lines bend. So carbon's here, 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 and here. The line between the two carbons is just like before, showing the covalent bond between the two molecules. And so carbon is shown at every end and at every bend in this drawing. But we know from the honk rule that carbon has to always form 4 bonds. So that means, or we should be thinking right now, that none of these carbons are happy yet. And this molecule must be happy if it exists in nature. It must have a very good full octet. So we're going to always fill in any open spots in this 4 bond rule for carbon with carbon's favorite partner, which is hydrogen. So in the molecule below, anytime we see a carbon, like right here, we're going to always fill in any open spots with a hydrogen. Carbon in this current picture right now is forming 1 bond. So we know that carbon's going to want to form 3 more bonds to be happy, and we're going to fill in a hydrogen at each bond opening. This carbon over here right now is making just 1 bond. So we know it's going to make 3 more bonds to be happy and get a full octet, and each of those bonds is going to be to a hydrogen. You can already see how much faster it is not to have to draw on every single carbon and every single hydrogen in these pictures. We're saving so much time. But it's not just the carbons at the end that we need to fill in, it's also these ones at all of the bends. So let's just do one of them as an example. Right now, this carbon right here at the top of this bend is making 1, 2 bonds, and we know it needs to get to 4. So we're going to draw 2 bonds at the top, and we're going to fill in with its favorite partner, hydrogen. And we could repeat this at every single carbon in the molecule, getting it to 4 bonds to fulfill the octet rule. And you're going to see that this simple original zigzag that eventually or at the beginning looked like this is now really this more complex molecule that has lots of carbons and hydrogens in the chain. And this is going to let us draw the structure quickly and efficiently, but we know when we see it in biology or in college chemistry or organic chemistry one day in grad school that there's really a lot more to these pictures. Okay, so that one got pretty messy pretty quickly. So let's start with a more simple picture. This one is on your paper. This is a picture of example A, and this is propane. You've hopefully heard of propane in your everyday life. If you have an outdoor grill, maybe you have a propane tank. When you walk into Lowe's or Home Depot, there's a place to return your propane tank. Propane is a really common fuel that people use to power all sorts of things in their houses. Propane seems to have a really simple small structure. We can already see from the size of this chain that this is not a gigantic molecule, but we want to fill it in so we can see every single atom in this hydrocarbon. So we want to remember the rule about carbon. Carbon always comes at ends and at bends. So on your drawing, let's draw in all the carbons that we know are in this structure. Here's an end, so we know it's a carbon, and carbon, and carbon. We now know that once we have all our carbons in there, we're going to fill in any open spots in the octet with hydrogens, because in a hydrocarbon, carbon loves to form bonds to hydrogens. So I like to start by finding a carbon, like right here, and figuring out how many bonds is it currently making. It looks like this one is making one bond. So I'm going to draw 3 lines off of carbon because I know it's going to make 3 bonds, and then I'm just going to put a hydrogen in every spot around the carbon. This carbon up in the middle is making 1 bond on the left and 1 bond on the right. So I know in order to get to the 4 bonds, as true from the honk rule, it needs to make 2 more bonds. So I draw my 2 lines and then I fill in with hydrogen. Finally, we have this last carbon over here. This carbon is making 1 bond. We know that carbon needs to make 3 more to get to a full octet, and then we're going to fill in with hydrogen. Next time you're grilling up a burger or you're returning your propane tank to the store, you will hopefully start to think about what's inside that tank, and it's millions and millions and millions of propane molecules that are a 3-carbon chain with lots of hydrogens attached. Almost every fuel, from your gasoline to methane, which comes out of the gas jets in our chemistry room, is made up of a hydrocarbon, a carbon chain with lots of hydrogens attached. We can already see this molecule is much more complicated and much larger, and it's no longer a hydrocarbon because it has oxygens in it. It's still an organic molecule because there's lots of carbons in this molecule, and there's even a carbon ring in here, which is pretty exciting. And this is a really common molecule in most of your houses. This is aspirin. So you might take aspirin when you have a headache, or maybe your grandparents take aspirin to help with their heart. And aspirin, as we can see, is a much larger molecule than propane, the fuel in your grills outside, and it has a lot more going on that we're going to have to try and analyze when we're filling in the missing carbons and hydrogens. Let's start by following the rule we have for carbons, which is carbon always shows up at ends and at bends. So let's just start by filling in any missing carbons. So I'm going to start over here on the right side, and here's an end, so I'm going to put a carbon, bend, carbon. Once I get to this bend, I can see that there's an oxygen there. So I can't replace the oxygen with carbon, so I'm just going to skip this. This is not an empty or an open spot. I'm going to get to here. There's a junction, so I'm going to put carbon, carbon at every bend around this ring. We'll talk about the ring more in a second. And here's another junction up here. None of these spots are open, so I'm going to leave those ends because they're not true ends. There's oxygens at either end. And we can see that aspirin is 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. And it has 1, 2, 3, 4 oxygens. And we know it probably has lots more hydrogens, but they're not all drawn yet. So let's complete the molecule so we can get the correct formula. Okay, so let's start this carbon at the end. It's always easiest to start there. This carbon currently is making 1 bond, and we know it wants to make 4. So 2, 3, 4, and I'm going to add in my hydrogens. That should seem pretty familiar from the step before. This next carbon, though, looks pretty interesting. Right now, this carbon is making 1 bond, 2, 3, 4. We know this double bond down here is 2 bonds, 3, 4. So this carbon is happy, which means it has no empty spots for hydrogen to be attached. So we're going to move on to our next carbon. Our next carbon right here, let's count the bonds that are sticking off the carbon. 1, 2, 3, 4. This carbon seems good. What about the carbon down below it, right here? This carbon makes 1, 2, 3. This carbon is going to need another hydrogen, so we're going to draw it sticking off the side. We can continue to go around the ring. This carbon is making 1, 2, 3. So let's draw another hydrogen. What about this carbon right here? 1, 2, 3. Let's draw another hydrogen. This is a very typical thing you're going to see in rings, where we have these carbon rings with the alternating single and double bonds with lots of hydrogen sticking off. Let's keep going. Here's a carbon. 1, 2, 3. So you need a hydrogen. And then here's a carbon. Let's count this one. 1, 2, 3, 4. So this carbon is all set. What about the last carbon, the one on the top up here? 1, 2, 3, 4. This carbon is all set. We're not going to draw anything sticking off the oxygen. The rule is only about carbons and hydrogens. Any other atom's going to get drawn in, so we're going to leave those alone. And we can now count up and figure out our formula. How many carbons are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. And what about hydrogens? How many hydrogens are in your picture? 1, 2, 3, 4, 5, 6, 7, 8. Don't forget this one up here. It's already drawn in for you, so H8. And then what about oxygens? What do we have for oxygens? 1, 2, 3, 4. This is the formula and the structure of aspirin. So next time you go home and look at your medicine cabinet, this is the giant large molecule that you're ingesting that will help with inflammation and headaches and all sorts of issues going on in your body.